Semester 1 Review, Honors Chemistry. You can access this review and this video at srhschem.wikispaces.com or on YouTube channel LEFFELlabs. The first section deals with bonding. In the first problem, we are asked to consider sodium chloride, water, and nitrogen, and for each formula, we need to draw the Lewis dot structure, determine the type of bond present, and if we have a covalent molecule, we have to determine the VSEPR shape. So first, we'll start with sodium chloride. So I need to determine how many valence electrons sodium and chlorine have. So if we check our table of elements, sodium is in the first group, meaning it has 1 valence electron, and chlorine is in group 17, meaning that it will have 7 valence electrons. So I can go ahead and draw in my electrons. There's 1 for sodium and 7 for chlorine. Notice that we followed a top right, bottom left pattern to fill in the electrons. We want to make sure that there are 6 of them that are paired and 1 that is unpaired. So in this case, we have a metal, and metals always give up electrons. So sodium is going to transfer 1 of its electrons to chloride. So because sodium lost an electron, it's going to form a cation with a +1 charge. The chloride, on the other hand, gained an electron, and when you gain a negative electron, your charge becomes -1. So to put it all together, we have our sodium and our chloride with our +1 and -1 charge, and we put brackets around the anion. So this is going to be an ionic compound, and we know that because we've got sodium, which is a metal, and chloride, which is a nonmetal. So anytime we have those together, we'll have an ionic compound. Next, we have H2O, so 2 hydrogens and 1 oxygen. So if we look on our table of elements, hydrogen is in group 1, which means 1 valence electron, and oxygen is in group 16, which is going to mean 6 valence electrons. So I'm going to put 1 electron for each hydrogen and 6 electrons for oxygen. So now that we've got all nonmetals, this is going to be a covalent compound, which means that I'm going to have to figure out how many bonds I can form and what the central atom will be. So hydrogen can have a maximum of 2 electrons, meaning that this 1 unpaired electron can form 1 bond. Oxygen has 2 unpaired electrons, meaning it can form 2 bonds. My central atom is always going to be the atom with the fewest number of valence electrons, but never hydrogen. So because we only have hydrogen and oxygen, our only choice is oxygen. So oxygen is my central atom, and I have to attach 2 hydrogens to that. And I have 2 bonds to do it with, 1 bond for each hydrogen. So that means that I'm going to use 2 single bonds. This molecule is polar covalent. I know that it is covalent because it's all nonmetals, and I know it's polar because if I cut it in half, it's asymmetrical. So anytime we have a molecule that is asymmetric, we can say that it's polar. Next, I have to determine what the shape of this is going to be because it is a covalent molecule. So I got my central atom, which is oxygen, and there are 2 bonding pairs. So that's going to be the hydrogens, and then the 2 lone pairs. So we've got the 2 oxygen electrons, the 2 red pairs that are together. So if we check our VSEPR theory is just a way to predict the 3D shape of molecules based on their Lewis dot structures. So this is only for molecules, only for covalent compounds. So each bonding or lone pair of electrons, they're trying to arrange themselves so that they're far away from each other as possible, so that they minimize the repulsion they have for each other. So the number of bonded atoms on my central atom was 2, and my lone pairs was 2, meaning that the shape of this molecule would be bent. Last one is nitrogen. So we've got N2. So I'm going to have 2 nitrogens, and if I check my table of elements, nitrogen is in column 15, which means it has 5 valence electrons. And there's 2 of them because we have N2. So each of these nitrogens has 3 unpaired electrons, meaning that they can form 3 bonds. So I've got 2 nitrogens, and I have to connect them using 3 bonds. So that's easy enough. That's just a triple bond. So a single bond is 2 electrons, a double bond is 4, and a triple bond is 6. So for each nitrogen, I've drawn 3 of the 5 electrons. The other 2 electrons that are up top, those are paired. So I'm going to put those together as a lone pair. This is going to be nonpolar covalent. I know that it's covalent because nitrogen and nitrogen are both nonmetals. And I know that it's covalent or nonpolar because if I cut it in half, it's highly symmetrical, which means that it's nonpolar. As far as the shape goes, I only have 2 atoms. So the way that you can connect 2 points is with a line. So this is going to be linear shape. Number 2 is a chart for us to complete about bonding theories. So for the first one, I'm told that it is a metal and a nonmetal, or there is a polyatomic ion. So that's going to be an ionic bond. So in an ionic bond, this is what we talked about with sodium chloride, the metal transfers an electron to the nonmetal. So the metal, having lost an electron, becomes a cation, and the nonmetal, which gained an electron, becomes an anion. These oppositely charged ions are going to attract each other, and that's the ionic bond. The next one is metallic bond. So in a metallic bond, we're going to have 2 or more metals that are sharing electrons in an electron C. So each metal atom is going to give up its extra valence electrons, causing it to form cations. Those electrons are then shared in an electron C between all cations. So these bonds are very, very strong because there's this constant attraction between those metal cations and the electron C. For the next one, I'm told that the electrons are being shared equally in a single, double, or triple bond. So this is going to be nonpolar covalent. I know that it's covalent because we're talking about sharing electrons, and it's nonpolar because we're sharing those electrons equally. This occurs between nonmetals. The last one, the only one that we have left, would be polar covalent. So this is where electrons are shared unequally in a single, double, or triple bond. So a couple ways to tell if something is polar or nonpolar. One is symmetry. The other is by electronegativities. So if one atom is more electronegative than the other, it's going to pull harder on those shared electrons in the bond. So we end up with a region where their electrons are spending more time, it becomes partially negative, and a region where there are less electrons becoming partially positive. So that's how we get the polarity. Number 3, we are given some substances, and they're all solids, and we need to, based on their properties, determine what type of bond is present in each substance. So the first one, substance A, is going to be ionic. So it dissolves in polar solvent. Ionic compounds are made of charges, so anything with charges can dissolve in polar solvent. So think of salt. That would be an ionic compound. We know that that dissolves in polar solvent like water, but it doesn't dissolve in a nonpolar solvent like oil. In an ionic compound, as a solid, the charges are stuck in place. Those ions are unable to move, so we get no conduction. They also have very high melting and boiling points due to their very stable structure made of positive and negative charges. B is going to be nonpolar covalent. So it dissolves in nonpolar, so you should remember like dissolves like, so this thing must be nonpolar. And it has no conduction because covalent compounds don't have charges, and they're going to have a relatively low melting and boiling point. Substance C is metallic because it doesn't dissolve in either polar or nonpolar solvent, and it is an excellent conductor. So that's due to the electron C, which is already made up of moving electrons, moving charges, which can carry a current. And metals have very high melting and boiling point due to that very strong attraction between the cations and the electron C. Number 4 is asking us to use the electronegativity difference to determine the bond type. So my first element is calcium, and I've got chlorine. So if I find the difference there, that's going to be a difference of 2. You can do the absolute value whenever you subtract them. I just want to know how different they are. So whenever we have a difference of 2, we're either going to be on the edge of very polar covalent or ionic. Because calcium is a metal and chlorine is a nonmetal, that means this is going to be ionic. The next one I have is carbon and hydrogen. So the electronegativity difference between those two is going to be 0.4. So once again, we're kind of on that line between polar covalent and moderately polar covalent. So given that carbon and hydrogen are pretty far apart on the table of elements, we're going to say that this is polar covalent. Now we're just looking at a single bond here. The molecule, it depends on which way the polarities are pulling in each bond. That's what's going to dictate whether or not the whole molecule is polar or not. The next one, I've got oxygen and oxygen, so that's obviously a difference of 0. So that definitely is going to be nonpolar covalent. Please note that regardless of the value of the difference, if you have a metal and a nonmetal, that will be ionic, and a nonmetal and a nonmetal will be covalent. The electronegativity difference range is a spectrum. So it goes from being absolutely not polar at all to ionic, which is like very, very, very polar. So there is a range, and bonds fall along that range. It is a spectrum. Number 5 says to determine if the bond that will form is ionic, metallic, or covalent based on the types of atoms. So for the first one, we have iron, which is a metal, and oxygen, which is a nonmetal. So whenever we have a metal and a nonmetal, that's going to be an ionic bond. The next one, I have sodium and magnesium, which are both metals. So this would form a metallic bond. And the last one, I have oxygen and another oxygen. And since both are nonmetals, those are going to be covalent. Number 6 asks us to use the electron C to explain the properties of metals. So here I have a bunch of aluminum atoms. So this is a metal, bunch of aluminum. And each metal atom is going to give up its electrons to the electron C, forming cations. So these all became cations plus 3 because they all gave up 3 electrons. Now those electrons are being shared by all of the aluminum cations. So there's this constant attraction between the cations and the negative electron C that makes metallic bonds very strong. So metals are malleable and ductile. If you strike them with some force, those cations are able to slide past each other. Normally, if you hit something and you push together those positive cations, that's going to cause them to repel and shatter. But because these electrons are flowing in between the cations, it insulates those positive charges from touching each other. So the electron C allows this to be malleable. Metals are also shiny, and that's because these free moving electrons, they can easily absorb and re-emit light. And metals are going to be good conductors because the electrons are already free moving. This means that they are able to carry a charge. Number 7 is asking us to explain what happens when a metal combines with a nonmetal in terms of electrons. So what I'm basically asking here is, how does an ionic bond form? So let's look at calcium chloride. So metals lose electrons to form cations. So this calcium is going to give up its electrons. Whenever you lose electrons, you become a cation. In this case, it's going to be +2. Nonmetals gain electrons to form anions. So each nonmetal gained 1 electron, making them each -1. Now we have opposite charges, and those charges attract to form a bond. So metals always react by losing electrons, forming cations. Nonmetals always react by forming anions. Number 8, why does an ionic compound conduct when dissolved in water, but not as a solid? So in order to conduct, we have to meet 2 conditions. 1, there has to be charges, and they have to be able to move. So an ionic compound as a solid is already made up of charges. It's made up of ions. But these ions are stuck in the crystal lattice structure of the ionic solid, meaning they can't move. If we add an ionic compound to water, the ions are going to dissociate. So now they're able to move in solution. So now it will conduct. Number 9 is asking about the phrase like dissolves like. So this is just a rule of thumb. It's kind of an oversimplification, but it helps us to remember what will dissolve in what. So a solute is going to best dissolve in a solvent that has a similar polarity to itself. And polarity is due to chemical structure. So anything charged, whether it's ionic or polar covalent, that will dissolve in something that is polar, like water. So an ionic compound like salt or a polar covalent compound like sugar will dissolve in a polar solvent like water. Anything that doesn't have a charge, this would be nonpolar. Nonpolar will only dissolve in nonpolar. So something like oil. Number 10 asks us to determine the VSEPR shape. So first I've got CH4. Carbon has 4 electrons, meaning it can form 4 bonds. Each hydrogen has 1 electron, meaning it can form 1 bond. My central atom is always going to be the one with the fewest valence electrons, but never hydrogen. So in this case, carbon is my central atom. And I have to connect 4 hydrogens using 4 bonds. So that's going to be single bonds all the way around. So my central atom is carbon. And there are 4 bonding pairs on the central atom. So there's 4 single bonds. Carbon has 4 valence electrons, and all of them are involved in a bond. So we have no lone pairs. So we can check our VSEPR sheet, and we see that that is a tetrahedral shape. Next is H2S. So S has 6 valence electrons, 2 of which are unpaired. So that's going to be 2 bonds. Hydrogen has 1 electron, meaning they can form 1 bond. So my central atom is going to be sulfur, and I have to attach 2 hydrogens to that using 2 bonds. So my central atom is sulfur. There are 2 bonding pairs on the central atom, so 2 single bonds with the hydrogens. Sulfur also has 2 lone pairs, so the 2 blue electrons that are paired together, that's a lone pair. So I have 2 of those lone pairs on sulfur. So according to our VSEPR sheet, that shape is going to be bent. Number 11, what do the dots in a Lewis dot structure represent? So this tells us the number of valence electrons of an atom. So everything in the first group has 1, the second group has 2, 3, 4, 5, 6, 7, 8. So boron has 3. Helium is technically a noble gas, but helium can only hold 2 electrons. So that's why they're drawn paired together like that, because it's a noble gas and it can't form any bonds. Aluminum is in the same column as boron, so we get a similar Lewis dot structure. Argon can have up to 8, and it's a noble gas, so it has all 8. So the fact that all of those electrons are paired, that's a closed shell. This is why noble gases are very non-reactive. The next section is about naming and formula writing. So first we have to determine if we have something that is ionic covalent or an acid, because there's a different set of rules for naming each of those, and then we have to write either the name or the formula. The first one that I have is sodium carbonate. So sodium is a metal and carbonate is a polyatomic ion. So this is definitely going to be an ionic compound. So sodium is Na with a +1 charge. And carbonate is a polyatomic ion, CO3 with a -2 charge. So I always need to make ionic compounds have an overall charge of 0. So I can do that by bringing this 2 down here. So that gives me +2, and the carbonate is -2, so that's neutral, and our formula is Na2CO3. Next I have P4HO10. So this is going to be covalent because I have 2 nonmetals, phosphorus and oxygen. So whenever I name these, I use my prefixes. So the prefix for 4 is tetra, and the prefix for 10 is deca. So this is just tetraphosphorus deca oxide. Next one that I have is obviously an acid because it has the name acid. Whenever we name an acid, we have to look at the form. So this is phosphoric acid, a blank-ic acid, which means that phosphor originally ended with 8. So I originally had phosphate. So phosphate is a polyatomic ion. It's PO4, that's 1 phosphate, and its charge is -3. This is an acid, so H goes in front, and H has a +1 charge. So in order for this to be charge neutral, I need 3 hydrogens. That's going to give me a +3 charge, which balances out the -3 charge from the phosphate. So H3PO4 is phosphoric acid. Next one, I have FeSO4. So this is ionic, and I know that because I have iron, which is a metal, and SO4 is a polyatomic ion sulfate. Now, iron is a transition metal, so that means that we have to indicate the charge using Roman numerals. So I don't know the charge on iron, but I do know that sulfate has a -2 charge. So my positive charge to balance that must be +2. There's only one iron, so the charge on that iron must be +2. So I've got iron 2 sulfate. Next, I have perchloric acid. So I have an acid because it says acid in the name. And I need to look at the form. So I have a blank-ic acid, which means that perchlor was originally perchlorate. Perchlorate is a polyatomic ion. It's ClO4, and its charge is -1. Because this is an acid, we're going to put an H in front. So that gives me +1 and -1. It's already charge neutral. So my formula is HClO4. Next up, I have H2CrO4. So this is an acid, and I know that it's an acid because it starts with H. So whenever you go to name an acid from a formula, you have to look at the thing that isn't hydrogen. That's chromate. Whenever you have ATE, that matches up to blank-ic acid. So it's going to become chromic acid. Next, we have cobalt-2 bromide. So this is going to be an ionic compound. Cobalt is a transition metal, and bromide is a nonmetal. So I've got cobalt, which is CO, and the charge on this is going to be +2, as indicated by the Roman numeral. Bromide is Br with a -1 charge. It's a halogen. So in order to make this charge neutral, I need 2 bromines to give me a negative charge of -2 to balance out the +2 charge of cobalt. So my formula is COBr2. Next, I have an ionic compound. So the name of this is going to be lithium acetate. I know that it's ionic because I have lithium, which is a metal, and acetate is a polyatomic ion. So this will be an ionic compound named lithium acetate. Next, I have copper 3 sulfate. So this is an ionic compound. I have copper, which is a transition metal with a +3 charge, and sulfate is a polyatomic ion with a -2 charge. So in order to make this charge neutral, I'm going for 6. So I want +6 and -6 because I've got +3 and -2. So if I bring the 2 after copper, that gives me +3 and +3, which is +6. And if I bring the 3 after sulfate, that gives me -2, -2, -2, which is a total of -6. So Cu2SO4 3. I need that Roman numeral around the sulfate because I'm trying to say there's 3 sulfates, not SO43. Next one is going to be an acid. I know that because it starts with hydrogen. So whenever you're naming an acid from the formula, you have to look at the thing that isn't hydrogen. So in this case, we have cyanide. An ending of IDE corresponds to hydroblankic acid. So we're going to get hydrocyanic acid. Next, I have aluminum hydroxide. This is an ionic compound, and I know that because I've got aluminum, which is a metal with a +3 charge, and hydroxide is a polyatomic ion with a -1 charge. So to make this charge neutral, I need 3 hydroxides to give me -3 to balance out the +3 from aluminum. So that gives me AlOH3. I need that parenthesis because I'm trying to say that there's 3 hydroxides, not that the formula is OH3. Last one is Cu3PO4, which is ionic. I've got copper, which is a transition metal, so I need to use a Roman numeral in the name. And I've got the polyatomic ion phosphate. So the charge for phosphate is -3. So the total positive charge that I need to balance that out is +3. There's 3 coppers. So if each of those coppers is +1, and there's 3 of them, that gives me +3 total. So the name of this would be copper 1 phosphate. Next problem has us to look at each of the following and determine if the formula is correct or incorrect. And if it is incorrect, we need to fix it. So these are all going to be ionic compounds. So we need to look at the charges to figure out if our formula is correct. So calcium has a +2 charge and chlorine has a -1 charge, meaning I should have 2 chlorines to balance out the +2 of the calcium. So that one was incorrect. The next one, I have ammonium, which is NH4 with a +1 charge, and nitrate with a -1 charge. So that's good. That is charge neutral. The next one, hydrogen has a charge of +1, and there's 2 of them. So my total positive charge is +2. Cyanide has a charge of -1. So that doesn't work because I have +2 from the 2 hydrogens and -1 from cyanide. So I should have HCN. The next one, sodium has a +1 charge and chromate has a -2 charge. So I should have 2 sodiums to balance out the -2 from the chromium. The next one, calcium has a +2 charge and each hydroxide is -1. So the total, because there's 2 of them, that gives me -2. So that one is okay. Last one, barium has a charge of +2, whereas hydrogen carbonate has a charge of -1. So I need to have 2 hydrogen carbonates in order to balance out the +2 from barium. The next one, we're given a bunch of name formula pairs, and we have to figure out which ones are incorrect, and if they are incorrect, we have to change it so that it is. So first one I have is CaBr, which is calcium and bromide, but calcium is +2 and bromide is -1. So calcium bromide should really be CaBr2. The next one I have BaSO4, and we say that that's barium nitrate. So the problem here is that nitrate isn't what we have. We have SO4, which is sulfate. So the name of this should be barium sulfate. FeCl2, and we're calling that iron 3 chloride. So the charge on iron is +2 because chlorine has a -1 charge and there's 2 of them, so iron must have a charge of +2. So this isn't iron 3 chloride, it's iron 2 chloride. Next I have carbon disulfide. So this is CS. Di means 2. I don't have 2, I only have 1. So this should really be called carbon monosulfide. Next I have KNO2, and we're calling that potassium nitrate. So nitrate's not correct. Nitrate is NO3. I have NO2. So 1 less oxygen means that it's potassium nitrite. The ite ending has 1 less oxygen than the ate ending. And lastly, I have H2SO4, and we're calling that hydrosulfuric acid. So whenever I name an acid, I gotta look at the thing that isn't hydrogen. So SO4 is sulfate. So the name that matches up to that is going to be sulfuric acid. There's no hydro because I have sulfate, and Blaikic acid matches up to the ate ending. The next section is about chemical reactions. So number 15 asks us about the law of conservation of mass, or the law of conservation of matter. So during any chemical or physical change, the total mass before and after is going to be the same. This took us a long time to figure out because we didn't have instrumentation that was fine enough to detect the exact mass. And a lot of chemical reactions, you'll produce a gas or something that escapes, So unless you're very careful, it's difficult to collect all of the matter. But if you're able to do so, you see that it's the same before and after. Another statement of this is that matter is neither created nor destroyed. So a balanced chemical equation shows this principle. Whenever you're balancing a chemical equation, you're making the moles of each reactant element equal to the moles of each product element. In other words, the moles of everything is the same, so the mass of everything is the same. Number 15, we are identifying the number and type of each atom in the formulas. So for the first one, I've got calcium, and there's 3 of them. Then after that, I have PO4 with a 2. So that means that there's 2 PO4s. So that gives me 2 phosphoruses and 8 oxygens. On the next one, we start off with our 3 carbons, and then we see that hydrogen is in 2 places. So I have H5, and then I have OH with a 3 after it. So that means 3 hydroxides, which means 3 hydrogens, a total of 8. And oxygen will have 3. The next one, I've got NH4 with a 2 after it. So that's saying that there's 2 ammoniums. So 2 nitrogens, 4 hydrogens for each. So times 2 gives me 8. There's 1 chromium and 4 oxygens. For number 17, we need to balance the chemical reaction and indicate the type of reaction. So to balance, first we can draw our line. We've got nitrogen and oxygen. And we can count, so 2 and 2 and 1 and 1. So this is really easy to fix. I just need to put a 2 in front of the NO, and that gives me 2 nitrogen and 2 oxygen, which balances the reactant side. This is going to be a combination reaction. B says that solid baking soda, which is sodium bicarbonate, is heated where it forms carbon dioxide gas, water vapor, and sodium oxide. So sodium bicarbonate is an ionic compound. Sodium is +1 and bicarbonate is -1. So my formula is just NaHCO3. Carbon dioxide is CO2. Water is H2O. Sodium oxide is ionic. Sodium is +1 and oxide is -2. So I know that I need 2 sodiums and 1 oxygen. So I've got sodium, hydrogen, carbon, and oxygen. So 1 sodium, 1 hydrogen, and 1 carbon, and 3 oxygens. And on the other side, 2 sodiums, 2 hydrogens, 1 carbon, and 4 oxygens. Make sure you're counting oxygen. It appears in 3 places: carbon dioxide, water, and sodium oxide. So I'm going to start by putting a 2 in front of NaHCO3. So that's going to give me 2 sodium, hydrogen, and carbon, but it's going to give me 6 oxygen. So in order to fix that, if I put a 2 in front of CO2, that gives me 2 carbon, but also 4 oxygen, plus the oxygen from water and from sodium oxide gives me 6. So now we're balanced. This is a decomposition reaction. The next one we need to balance. So I've got iron, chlorine, sodium, and I've got hydroxide on both sides. So instead of splitting that up into H and O, I'm just going to keep it together because it appears on both sides. 1 iron, 3 chlorines, 1 sodium, 1 hydroxide. On the other side, I've got 1 iron, 1 chlorine, 1 sodium, and 3 hydroxides. So I'm going to start by putting a 3 in front of the NaCl. So that gives me 3 sodiums and 3 chlorines. Then I'm going to come to the other side and put a 3 in front of NaOH. So that gives me 3 sodium and 3 hydroxide. And now we're balanced. This is a double replacement reaction. For D, sodium phosphate is reacting with calcium chloride to form calcium phosphate and sodium chloride. So these are all ionic compounds, which means we have to make sure that the charges are neutral on all of them. So sodium phosphate, I'm going to get 3 sodiums for every 1 phosphate. Calcium chloride is CaCl2. Calcium phosphate, so I've got +2 and -3. So I'm going to aim for 6 on each side. So 3 calciums gives me +6 and 2 phosphate gives me -6. And last, I've got sodium chloride, which is just +1 and -1. So I've got sodium. PO4 phosphate appears on both sides, so I'm just going to keep that together to make things simpler. Then I've got calcium and chlorine. So 3 sodiums, 1 phosphate, 1 calcium, 2 chlorines, 1 sodium, 2 phosphate, 3 calcium, and 1 chloride. So I'm going to start this out by changing the Na3PO4, putting a 2 in front. So that gives me 2 PO4s, but it also gives me 6 sodiums. So now I'm going to fix the calcium. If I put a 3, that will give me 3 calciums and 6 chlorides. So we can wrap everything up by putting a 6 in front of NaCl, giving me 6 and 6. And now we're balanced, and this is a double replacement reaction. The last one, I've got carbon, hydrogen, and oxygen. So 3 carbons, 8 hydrogens, and 2 oxygens. And on the other side, I've got 1 carbon, 2 hydrogens, and 3 oxygens. So to balance this out, first thing I'm going to do is put a 3 in front of the CO2. So that gives me 3 carbons, but that gives me 6 oxygens plus the 1 from water, gives me a total of 7. Now let's do hydrogen. So if I put a 4, that gives me 8 hydrogens, but it also gives me 4 oxygens. So the 4 from water plus the 6 from carbon dioxide give me a total of 10. So to balance this, if I put a 5 in front of the O2, that gives me a 10. This is a combustion reaction. Number 18 asks us to construct an activity series based on the experiment data that is given. So B will have a reaction with A NO3, C NO3, and D NO3. So that means that it can replace all of those elements. A can only replace C and D will only replace C. C isn't reactive enough to replace anything. So with most reactions, I've got B as the most reactive metal, and my least reactive metal is going to be C. Number 19 says that based on the activity series that we just made, which metal, X, can replace D in the chemical reaction? So in order for the reaction to occur, the lone element X has to be more reactive than element D, which is in the compound. So based on our activity series that we just constructed, X can be anything above D on the activity series. So it could be B or it could be A. Number 20 is asking us to summarize the different types of chemical reactions. So first I have A and B combine to make AB. So this is a combination reaction where 2 or more reactants combine together to make one product. Decomposition is the exact opposite, where we start with one reactant and it breaks down into 2 or more simpler products. For the next one, I'm told that a lone element replaces a less reactive element in a compound. So this is going to be a single replacement reaction, which we just saw with the activity series. So A is able to replace B in the compound only if A is more reactive than B. Next is double replacement. So this is going to occur between 2 ionic compounds that switch cations, and this occurs in aqueous solution. So they're kind of like switching dance partners. So instead of A with B, now A is with D and C is with B. Last one is a combustion reaction. I start with a hydrocarbon, that's what CXHYOZ is, and it reacts with oxygen to form carbon dioxide and water. The next section is about periodic trends. So on number 21, we're asked to color code the metals, the nonmetals, and the metalloids. So metals are going to take up most of the table of elements. The metalloids touch the staircase, so that bold line, except for aluminum and polonium. And nonmetals will be everything else. So this allows us, based on their positions, we can predict what type of bond will form. Metals, most of the table, nonmetals are going to be to the other side of the staircase. Which elements are diatomic? So you can remember, have no fear of ice-cold beer. So the have is for hydrogen, no is for nitrogen, fear is for fluorine, of is oxygen, ice is iodide, cold is chlorine, beer is bromine. So anytime that you have like hydrogen, that's always H2, never H, or nitrogen is N2, never N. And this applies whenever they are by themselves. So in a compound, this rule doesn't apply. Number 23, summarize the properties of metals, nonmetals, and metalloids. So metals are going to be good conductors of heat and electricity. And this is going to be due to the free-flowing electron C that can carry current and heat. The electron C is going to allow the metal cations to easily slide past each other if they're struck with a force, so metals are malleable. Metals are going to be silvery, except for gold and copper, and they're going to be shiny and lustrous. Most will be solids, the main exception there being mercury. Nonmetals are poor conductors. They are brittle, so if you hit them with a hammer, they will shatter. They are not malleable. And they can be many colors, like copper is black, phosphorus can be red or white, sulfur is yellow. They're dull. Many of them are gases, and some of them are also solids. Metalloids are in between metals and nonmetals. So they're going to be semiconductor. They could be brittle or malleable. And some are shiny, some are dull. So they're just in between metals and nonmetals. 24, give examples of elements in the same family and in the same series. So a family, a group, a column, these are all interchangeable words. And I remember this because they're all at the beginning of the alphabet. So anything that's in the same column is going to be in the same family. A series, period, or row, these are all the same thing. They're all start with letters that are at the end of the alphabet. So anything that's in the same row is going to be in the same series. 25 is asking us about some group names. So alkaline metals are going to be in column 1. Column 18 are going to be our noble gases. Halogens are right next to them in column 17. And alkali earth metals are in column 2 next to the alkali metals. Halogens have very high ionization energy. Explain why. Ionization energy is the energy necessary to remove an electron from an atom. So if there's a very strong attraction between the electron and the nucleus, you need a lot of energy to pull it away. Halogens have 7 valence electrons. They're very, very close to having a full octet. So halogens are going to tend to be very attractive to electrons, meaning that it's very difficult to remove one. 27 is asking us to summarize the periodic trends. So first we have electronegativity. This is a measure of how strongly an atom can attract electrons. So the reason halogens have such high ionization energy is because they're very electronegative. They very strongly attract electrons. Atomic size and radius is the radius from the center of the atom to the outer edge of the electron cloud. First ionization energy is how much energy you need to remove the first electron. There's also a second ionization energy, a third ionization energy. And shielding effect is the blocking of the outer electrons from the nucleus by inner electrons. So it's kind of like you're at a concert and there's a bunch of people standing in front of you that are shielding you from the stage. So for electronegativity, as I go across a row, I'm getting more protons and I'm also getting closer to a full octet. So this means a stronger attraction, which means higher electronegativity. As you go down a group, we're getting more and more layers of electrons, so the shielding effect is increasing, meaning it's much harder to attract an electron. Electronegativity decreases. Atomic size, as we go across a series, there's more electrons that are pulling there's more protons that are pulling the electron cloud in closer. So because there's that stronger attraction, moves in closer, they get smaller. As you go down a group, down a column, we're getting more layers of electrons, so the size is going to get bigger. First ionization energy is going to increase as we move across a row. We're getting more protons, so the attraction is getting stronger. We're also getting much closer to full octet, so it's going to be harder to remove an electron. As we go down a group, however, those additional layers of electrons may make it much easier to pluck one away. The shielding effect is constant as we go across a row. This is because there are constant energy level across a row. So we're not getting any more layers, so the shielding effect stays the same. This is kind of like if you're at a concert, the people who are in the same row of you aren't going to cause any more shielding. If we go down a group, however, we're getting more and more layers, more energy levels, and this is going to cause the shielding effect to be much stronger. The next section is about subatomic particles. So number 28 is asking us to compare the proton, neutron, and electron. Protons are positive, neutrons are neutral, and electrons are negative. Protons and neutrons are both in the nucleus, and the electrons are orbiting the nucleus in electron clouds. Comparatively speaking, protons and neutrons are very heavy, and electrons are very light. So a proton or a neutron would be like an elephant, whereas an electron would be like a marble. Which subatomic particle is responsible for the chemical properties of an atom? So chemical bonds occur because atoms are sharing or transferring electrons. Thus, electrons determine the chemical properties of atoms. So it determines whether or not two atoms can bind together, whether or not chemical reactions occur. Number 30 uses isotope notation and asks us to fill in the blanks. So first we have the symbol. So the way that we write this is the number on top is the mass number, and the number on bottom is the atomic number. The symbol is just the symbol from the table of elements, and the charge is also indicated as a superscript. Atomic number and number of protons, those are the same thing. In order to find neutrons, we need to know the mass number and the number of protons. So the mass number is the sum of protons and neutrons. Those are the massive parts of the atom. So if I have the mass number and I subtract out the protons, I'm left with neutrons. For electrons, I need to look at the charge. So if I have a positive charge, it means I have more protons than electrons. If my charge is negative, I have more electrons than protons. And of course, mass number is just the sum of proton and neutron, the massive parts of the atom. So for my first one, my atomic number is 11, which means 11 protons. My mass number is 23. So to figure out the number of neutrons, I got to take 23 minus 11 protons, leaves me with 12 neutrons. The charge on this is +1, meaning there must be one more proton than electron. So I have 10 electrons. For the next one, my protons and my atomic number are the same. And my mass number is the sum of protons and neutrons, so 20 plus 21. That gives me 41. So for my symbol, I have mass number 41, atomic number 20 corresponds to calcium, which is Ca, and my number of protons and number of electrons are equal, meaning my charge is 0. So you can write the 0 or you can just leave it blank. The next one, I also have 20 protons, so the atomic number is 20. My mass number is 40, so if I subtract out 20 protons, I'm left with 20 neutrons. So this is also going to be calcium with a mass number of 40, and the charge is still 0 because I have 20 protons and 20 electrons. For D, my atomic number is 11, so I have 11 protons, and 11 protons plus 12 neutrons gives me 23 for my mass number. So this is also going to be sodium, so atomic number 11 with a mass number of 23, except this time the charge is 0. So what is an isotope? Isotopes are going to be atoms of the same element that have a different number of neutrons. So because they are the same element, they have the same atomic number, the same number of protons. But different number of neutrons causes their mass number to be different. So here are 3 isotopes of carbon. Carbon-12 has a mass number of 12 from 6 protons and 6 neutrons. Carbon-13 has 6 protons and 7 neutrons, so that gives me the 13. And carbon-14 has 6 protons and 8 neutrons, giving me the 14. So because they're all carbon, their protons are the same, 6, but they have different numbers of neutrons. So C and B are going to be isotopes of calcium. A and D are not isotopes because they have the same mass number. Which of the following has more electrons? So anytime you lose negative electrons, the charge becomes more positive. So Fe0 has the most electrons because it has not lost any and become a cation like the others. 31 is about Rutherford's experiment. So in Rutherford's experiment, he shot alpha particles at a thin layer of gold atoms. He expected that all of the alpha particles would fly through the gold atoms because at the time, plum pudding model was the accepted model of the atom. So this is just a sphere of positive charge with small electrons embedded within. So there is nothing in the plum pudding model of the atom that would cause any deflection from the alpha particles. But when he performed the experiment, he saw that some of the alpha particles bounced back. This led to Rutherford's model, also called the planetary model. So the reason the alpha particles fly through is because the atom is still mostly empty space. But they bounce back because there's something very dense and very positive in the middle of these atoms, which is called the nucleus. So to complete the alpha particle paths, we should show most of them going through the gold foil and a couple of them deflecting off of the nucleus. Number 32 is asking us what happens when an electron absorbs and re-emits energy. So this was figured out by Bohr, and this is called the Bohr Model. So electrons travel around the nucleus in energy levels. This is called their ground state. If I allow an electron to absorb energy, these energy levels are quantized, so there has to be just the right amount of energy. It will allow that electron to jump up in energy level. This is called the excited state, and it is unstable. So to regain stability, those electrons have to re-emit that extra energy to return to their ground state. Depending on how much the energy is that is released, depending on how big the jump was, it might be released in the form of visible light. This is what we see whenever we do a flame test. So these colors, these transitions, are unique for each element. So based on the pattern of the emission spectra, we can actually use this to identify what elements are present, for example, in a distant star. The next section is experimental methods. So in number 33, students wanted to determine how the amount of sodium would affect the amount of energy given off during the reaction of sodium with water. They measured out 1 gram, 2 grams, 3 grams, and 4 grams of sodium metal and added each to 500 milliliters of water. The amount of energy given off was then recorded. So first, what is the independent variable? So the independent variable is intentionally varied from trial to trial. In this case, they varied the amount of sodium. The dependent variable responds to the independent variable, and it's what we're measuring. So we measure the amount of energy released. In an experiment, the only things you want to change are the independent and dependent variables. So everything else should be a constant. It should stay the same for all trials. So the obvious one is the amount of water, 500 milliliters, but also they want to do it in the same conditions. They want to use the same measurement tools, the same scale, whatever they're using to measure the energy release should be the same. It should be the same kind of water from the same source. We're trying to make everything constant so that whenever my dependent variable changes, I know that it's only because of my independent variable. What is a possible question? So a scientific question is something that will include the independent and dependent variables. So something like, how does the mass of sodium affect the energy released when added to water? To measure out sodium, so sodium is a solid. We measure it in grams. So we're going to use a scale, like an electronic scale or a triple beam balance. What would the students use to measure out the water? So if we have a liquid, we use a graduated cylinder. We do not use a beaker. A beaker has lines on it, but those lines are very approximate. They're just printed on there. So a beaker would be for like carrying things or holding things, performing a reaction in. But if I need to measure out an exact amount of water, like 500 milliliters, I need to use a graduated cylinder. And which reactant contains only one type of atom? So that's going to be the sodium. Water has hydrogen and oxygen, which is two types of atoms. The next section is about intermolecular forces. So for number 34, first we need to identify the intermolecular forces that are present in each molecule. So dispersion forces occur in anything covalent. So as long as it's all nonmetals, we'll have dispersion forces. Dipole-dipole occurs in a polar covalent molecule. So we have to use symmetry or electronegativity difference to determine if it's polar or not. And hydrogen bonding is where we have an H bonded to an FO or N. So the H of one molecule will be attracted to the FO or N of another molecule, forming a hydrogen bond. So the first one, H2S, is going to have dispersion because we have nonmetals, it's covalent. And if I cut it in half, it's different on the two sides, meaning we have dipole-dipole. The next one is going to have all three. So we have water, which is covalent. It's also polar. If I cut it in half, it's different on each side. And I have H attached to an O, so it's also going to have hydrogen bonding. The next question, the boiling point of water is 100 degrees Celsius, while the boiling point of H2S is minus 60 degrees Celsius. So why do we have this difference? So water has hydrogen bonding. So in order for something to boil, we're just changing the liquid into a gas. So we need to interrupt those strong attractive forces so that the liquid can become a gas. We do that by adding heat. Now, since water has hydrogen bonding, we need much more heat energy to disrupt those very strong attractive forces in the liquid. This means that water will have a much higher boiling point because of the presence of hydrogen bonding. 35, which molecule is more likely to have a strong odor? So the fewer intermolecular forces there are, the weaker the attraction between the molecules is. So if this attraction is very weak, the molecules can easily escape each other, meaning that it's very easy for them to enter the air, causing a strong odor. So the first molecule only has dispersion, while the second molecule has all three forces. We have hydrogen bonding because we have that one little hydroxide group there. So between these two, the first one is going to have a stronger odor. The first one is gasoline, the second one is vanilla. So yes, vanilla does have an odor, but if I open a container of vanilla, you're not going to smell it across the room. If I open a container of gasoline, this is octane, that is going to definitely have a very strong smell. The next section is about mole calculations. So number 36, explain what Avogadro's number is. How do we use it? So Avogadro's number tells me how many things are in a mole. So it could be atoms or molecules or whatever, but there's always 6.02 times 10 to the 23rd things in a mole. Kind of like how there's always 12 things in a dozen. I don't care what it's a dozen of, it's always 12. So for a mole, I don't care what it's a mole of, it's always 6.02 times 10 to the 23rd. We use this to count atoms and other very, very small chemical quantities. So we count atoms using moles, kind of like how we count eggs using dozens. 37. So we've got a couple mole conversions to solve. How many moles are in a 35-gram sample of sodium chloride? So if we consult our mole roadmap, we want to know how many moles are in a certain mass. So in order to go from mass to moles, I need to use my molar mass. So I'm going to start with 35 grams of sodium chloride over 1. And I need to cancel out the grams, so grams goes on bottom and moles goes up top. So anytime you see grams and moles, you should think of the molar mass. So I find the molar mass of sodium and the molar mass of chloride. There's one of each, so I just have to add those up. And that's where we get that 58.443 grams. So whenever I solve this, I get 0.60 moles of NaCl. The next one, how many molecules are present in 15 liters of carbon dioxide? So this time we're starting at volume of gas with 15 liters, and I want to know how many molecules that is, which are the same thing as particles. So I need to convert my liters of gas into moles. So liters goes on bottom and moles goes up top. We call this conversion factor molar volume. Now I need to change moles into molecules. So this is Avogadro's number, the number of things that are in a mole. So whenever we solve, we get 4.03 times 10 to the 23rd molecules of carbon dioxide. Next one, how many grams are there in 2 moles of sodium atoms? So I'm starting with 2 moles and I need to get to grams. So this is just going to be a one-step conversion using molar mass. So I've got 2 moles of sodium. I need to put mole on bottom, and I'm looking for grams. So that's molar mass. The molar mass of sodium is 22.990. So whenever I solve, I get 45.98 grams of sodium. Next one, how many grams are present in 1.204 times 10 to the 24th atoms of iron? So I'm starting with atoms, which are particles, and I need to go from atoms to moles and then moles to mass. So this is a 2-step conversion problem. So I'll start with what I'm given over 1. I want to cancel out atoms, so that has to go on bottom, and mole goes up top. This conversion factor is just Avogadro's number, how many atoms are in a mole. Next, I need to take moles and change it into grams using the molar mass of iron, which is 55.847 grams per mole. So that gives me 111.694 grams of iron. Explain why a mole of silver and a mole of gold have the same number of atoms but different molar masses. So a mole is always 6.02 times 10 to the 23rd atoms. A mole of gold will weigh more than a mole of silver because a gold atom is heavier than a silver atom. So even though they have the same number of atoms, a gold atom is heavier than a silver atom. So the molar mass of silver is 107, and the molar mass of gold is 197. So it weighs much more. For percent by mass. So to find percent composition, we need to take the molar mass of the element, in this case oxygen, divided by the molar mass of the compound. So the molar mass of my compound, KMnO4, will go on bottom, and the molar mass of my oxygen will go up top. So I have to take the molar mass of oxygen and multiply it by 4 because it's O4. This gives me 40.49% oxygen. For water, we've got 15.999, which is the molar mass of oxygen, divided by the molar mass of the compound, which is water, and we get 88.81% oxygen. Last one, calcium oxide has a molar mass of 56.079, and the 1 oxygen is going to be 15.999. So this gives me a composition of 28.53% oxygen.